If you have multiple WAN ports in your UniFi gateway, you can set up load balancing. For the first option, failover, it's very easy to understand, but when it comes to distributed, you may wonder how it works during runtime, how the system decides which WAN port to use for a particular packet. In this video, let's discuss it. In my lab environment, I have a UXG Pro. It has two WAN ports. This gateway is behind the main router, so that's why for both WAN ports, the IP addresses are private IP addresses. But it doesn't matter. It doesn't impact the goal for this video. In the right side, you can see the two WAN ports. They have different IP addresses. They are all showing green. And in the diagram, you can see just to help us understand which WAN port is used for the traffic, I have two Wiresharks monitoring the two WAN ports respectively. In the LAN part, I have two Linux machines, and in the UniFi network controller, you can see I set the two WAN ports to load balancing distributed. I have 50-50 default setting at this moment. Now let me launch Wireshark. Okay, they are all up and running. I set the display filter to IP address 9999, so that's why you don't see any traffic in either Wireshark. Then in the right side Linux machine, from client 1, let me run dig command. I use 9999 as the DNS server. I want to query x.com. Okay, you can see the traffic hit the first WAN port. We see the captured packets in the first Wireshark, right? Then let me do the same thing in client 2, the same command. So the traffic goes to the second Wireshark. This is just a simple demo to see the load balancing distributed work in action, right? But there are two common confusions or misunderstandings about the distributed load balancing. First, some people may have two internet connections from two ISPs. So when they set the load balancing distributed, they expect the gateway use both ISP's service so that they can have the combined internet bandwidth. What those users expect is not really load balancing. They want one aggregation. They want to aggregate two WAN ports to achieve the wider bandwidth. That's not what load balancing is going to achieve. The second common misunderstanding is if they have very heavy internet activity, the users may expect the system will distribute the traffic to both WAN ports based on the ratio set here. It doesn't work that way. The reason is the WAN port selection is per connection. As long as your packets are in the same connection, they will and only will go via just one WAN port. It cannot be distributed into multiple WAN ports if the packets are from the same connection. So you can distribute the load for different connections among multiple WAN ports, but you cannot distribute the load for one connection among multiple WAN ports. You will understand why when we see in backend how it works. So we can easily validate the second confusion. Let me change the display filter. I have changed the display filter to an IP address because I am running a iPerf3 server at that IP address. From the two Linux clients, let me do the iPerf3 testing. I'm specifying this IP address as the server. Let me run iPerf3 in Linux client 1. Okay, so from the Wireshark, you can see all the traffic goes with the first WAN port. There's nothing in the second WAN port. Then let me run the same thing from Linux client 2, the same command. So this time you see two effects. They both showcase how the distributed load balancing works. First, you can see from the Linux client, I run the ipperf3 command. It runs for about 4 seconds. Tons of packets were generated, right? But all the packets went with the first WAN port. The traffic from the same connection was not distributed among the two WAN ports. The second thing it tells us is, remember when we do the dig command testing for Linux client 2, the traffic went with the second WAN port. right? But now I'm doing a ipperf3 testing. This time the traffic went with the first one part, not the second. As I said, the load balancing distributed works on the connection level, not on the client machine level, not on the packet level. It works on the connection level. Later you will understand when we dig deeper. Now it's time to try to understand how the distributed load balancing works in backend. Because we are talking about internet traffic routing, of course, we want to first check the routing tables. In Linux or in UniFi Gateway, you can use multiple related commands to check the routing related settings. In the lower part of the window, let me first SSH into the UXG Pro. Okay, you can use multiple commands to check the routing related settings in backend. For example, I can run IP rule. Okay, it will list a set of rules. Some of them are related to our today's video. For now, let's check another command, which is IP route. Here you can see some table contents from the main table. There are 3 built-in tables when you run IP route: the local table, main table, and the default table. They are not really so relevant to our today's video, but let me briefly mention them anyway. So local table has the high priority control routes for local and broadcast address. I can run IP route show table local. You can see all the local or broadcast related settings. Then the second table I can show you is the main table. This table may look familiar. Basically, it's talking about the important routing table. The Linux kernel will use this table when calculating routes. And then there's another table. It's called default table. Contrary to the name, this table in fact is reserved for post-processing rules. At this moment, you can see the UniFi Gateway simply has an empty default table. So these are 3 different built-in tables. And later we will see there are important custom tables due to our distributed load balancing setting. We will talk about that later. Okay, now let's look into the details of these 2 IP commands. Let me run IP rule. These are the rules generated by the system depending on our settings. We don't have time to go through all of them, just briefly check them. You can see the first column is a priority. 0 means the highest priority. Of course, it needs to follow the local table about the local and the broadcast related routing. And then it will follow the main table. All your familiar routing rules should exist in this main table. Okay, then you see 2 interesting settings. See, just from the interface name, you can guess these 2 may be related to our today's topic because they are about the 2 one parts, right? But you may not be familiar with this thing. It's called FW mark. It's a mark technique used by Linux kernel. This is super important. It will be the star for this video. It's because of the different marks. The system knows how to route different internet traffic through different one part. But we will go back to these 2 rules later. For these 4 rules, they are here simply because for the first one part, I have 4 IP addresses defined. If I go to the first one part, you can see I have 4 IP addresses. And then for the second one part, I have 2 different IP addresses. So that's why you see 4 rules here for the first one part and then 2 rules here for the second one part. Right? And then there's a rule. It's not related to this video. And then later you can see there are some kind of default internet rule. It is using the first one part. And then it is using the empty default table. Okay? So after reading these 2, we already know, okay, the distributed load balancing is somehow related to these 2 rules. But let's try to understand these 2 rules. So what it is saying is for all packets, if it meets this mark condition, the number before the slash means the mark itself, and then the second number after the slash is a mask. We will talk about the details later. If it meets this condition, right? It will use this table. So let's see what's this table about. We run the IP route command, then we say show table followed by the table name here, 201.add0. See, this is a super simple routing rule. To go to this external gateway, we need to use the first one part. That's it. It doesn't explain why we want to go through this part. It only says if you want to reach this one, you can use this one part. But in what condition? If the mark meet this condition. After looking these IP tables, we know some conditions, if they are met, the system will choose different one part. But we still don't know where this mark thing, where they come from, right? This leads to another super important thing within UniFi Gateway is IP tables. IP tables is a administration tool used to set up, maintain, and inspect the IP tables used by the Linux kernel when it does the IP packet filtering. The firewall rules you are familiar in UniFi Gateway. In fact, they are implemented using IP tables. Or the NAT rules, SNAT, DNAT, Masquerade NAT, they are all implemented using IP tables. And for the distributed load balancing, it's also implemented using IP tables. Let's look into the details. This is a simplified diagram showing how a packet goes from inside your local network step by step, how it is changed and then sent out to internet. By analyzing these steps, we can understand how the weighted load balancing works. And to make it even simpler, I grayed out the steps which don't really have relevant rules, which means we only need to analyze these 3 steps. Okay, let's start with this mangle pre-routing. In the UniFi Gateway, let me run this command. Here I want to show the mangle table content. There are 3 major tables in IP tables. The mangle table is used for packet alteration, which means the kernel will change something in your regular network packet. To be more specific, what kernel will change? It will change 2 different marks. First one is the regular mark. Every packet has its own mark. And then the second type of mark is connection mark. The system will make sure for all the packets which belong to the same connection, they will carry the same connection mark. There are different options, a little bit confusing. Restore means get the connection mark value, save to mark. And save action means get the mark and save to connection mark. You may not want to care about all the details, but just in case when you read the rules you are confused, you can take this as reference. Then let me display the mangle table content. Oh, sorry, it's line number, not number. So you see a lot of rules already. Just to help you understand what's going on, I draw this diagram. Basically, what the system does is, let's assume you have a brand new packet trying to send out to internet. Okay, the system goes to this step and then this step. Because initially the connection mark is nothing, so it will try to restore the mark, and then it goes to this step. For this step, it will first execute this chain. It's for the first one part. So if the connection state is new, which means it's the first time you send out the packet to the internet, it will simply mark a value, which is 1A. In the right corner, I note down the binary format of this value. The system will use these 3 numbers very frequently. If you compare 1A and 1C, you can see they are only different in these 2 digits, and the 7E is used as mask, so that's why it has all 1 in the interested bits. Okay, if it's a new packet, if it's from the first one part, it will set this value. But apparently this is not our case, because our case is from local network to internet, so not from internet to local network, right? So we can ignore this part. Let's go to this section. So for this section, let me show you the corresponding rules in the SSH session. Okay, it's here. So this chain is the main thing related to our video. It decides which one part to choose. So let's analyze them one by one. The first step, simply check whether the connection state is new or not. If it's not new, it will simply skip everything. For our case, because we want to see when a packet is new, right? Then let's move on. Following two rules, we are not interested. They are not relevant to our topic. Then move on. So the fourth rule is a mark target, and it will mark what? It will see whether the packet match this value using this mask, and here comes this very special probe name. So this is not a standard Linux match set. It is using this interesting name. You can already guess it is related to the weight we set on the UI, and it is related to whether to choose the first one part. And then the next rule is about the second one part, right? Apparently these two rules are the crucial things which decides which one part to use. Let's try to understand what's this thing about, the probe name thing. Because this probe name is in the match section of a rule, I assume it is a custom module used by Ubiquiti in the IP tables. So let me try to confirm that. Let me see what's in this folder. In the IP table matches, I should be able to see all the loaded modules, the standard one and the custom ones. Okay, so I do see familiar connection tracking, connection mark, limit, mark, set. There's a interesting one. It's called dyne random. The name suggests it's something related to dynamic random thing. This is the only possible module which is related to our probe name match. Let me try to see what's the description for this module. The way to find it out is I run iptables and I say module dyne random. Then I want to see the help. Okay, we do have one line help for this module. See, this is our friend, probe name. The description is match on probability. Even though we still don't know what's the technical details for this module, but at least we understand, okay, here the probe name, it's simply about probability name. It means the probability for a brand new packet to choose the first one part. That's the functional meaning for this match. Let me see whether I can drill down to more details. After a search in the file system, I found this folder. So there are two files under the folder. See, the file name is exactly as shown in our IP table rules, right? So let's try to see what's inside the file. Okay, for the first one part, it's a number. And for the second one part is another number. Because on the UI, we set the distributed load balancing as 50-50. It seems internally the system still need to randomly decide for a connection which one part to use, right? It seems the system generates some random number, and based on its own algorithm, which is not documented, we don't know how it works internally, but at least by using some random numbers, the system will choose which one part to use for a given new connection. Okay, so basically my investigation ends here. I don't have any way to furtherly find out the implementation details, and Ubiquiti doesn't have anything documented. But at least from functional perspective, now we already understand what these two rules are. Let me translate it to English. If by the probability algorithm, the system decide to choose the first one part, then the system will do what? The system will do a X set using this 1A number and with this mask. So the end result is in the mark, you will have a special bit set with 1. That's the end result of this rule. For the second one part, if by the probability algorithm, the system decides to choose the second one part, it will set using the 1C number. So which means the end result is the mark has another different bit set to 1. By choosing different one part, later the mark will be used to choose the non-new packet, which means you may not finish your connection just by using one packet, right? It's very possible you may have some follow-up packets. All the follow-up packets will use the same mark because the decision is already done when the connection state is new by using these 2 bits. Okay, this is just a brief explanation about what's happening in the mangle table. So let's go back to this diagram. In the very first step, for the iptables mangle table pre-routing, the system will use these marks to mark different bit depending on which one part is chosen. So once we are done with this step, it will go to the routing decision, which is the routing rules we already checked. Let me show you the routing rules again. Okay, remember these 2 old friends? Now we see how the 1A and 1C works in the mangle table, right? I believe it's clear because in the mangle table pre-routing step, the system already set the mark using either 1A or 1C. Then once we are in the routing decision step, the routing rule has a very simple job. If the mark is 1A, it will use this routing table, which means it will route through the first one part. If the mark bit is 1C, it will use another routing table, which means it will route through the second one part. That explains how the magic happens. A magic bit is set in the iptables pre-routing step. Then based on the special bit, the routing rule will decide which one part to choose. Then the flow is in this step, the very last step before the packet is going out of the local network. So here it will do the SNET. Remember, we are talking about accessing internet, right? So in the SNET rule, it will simply do the masquerade net to replace the IP address with the one part IP address. It is out of scope for this video. Once you have the IP address replaced with the one part IP address, the packet is ready to be sent out to the internet world. Okay, it is a very complicated data flow. Even though I already tried my best to simplify it, it's still very complicated. But the crucial step happens in the mangle table step, and the routing is simply use the result of the mangle table mark manipulation to decide which one part to use. Okay, this is a long video. Thanks for watching.